I have the unenviable task of following Bruce up, which is always a challenge. Today I just want to summarize a couple things from the lectures that we had yesterday on spatial frequency domain and spatially resolved reflectance methods, just to try to distill and crystallize the teaching objectives from yesterday, to remind you where you have sensitivity to the various optical properties and why that's the case and where in measurement space, and then kind of summarize or introduce those same concepts in temporally resolved and temporal frequency domain methods. So, and that will be, I think, reinforced both in the demos that we have this afternoon right after lunch and in the computational lab. Okay, so just a listing of what we hope to cover. So we'll talk about the principles underlying the use of pulsed and intensity modulated optical sources for time resolved and temporal frequency domain reflectance. I'm going to introduce the diffusion approximation because that's in a form that's specific to both the spatial domain as well as the temporal domain reflectance methods, because I think that gives you a nice way to understand sensitivity to optical properties, both in the spatial and temporal domains. And then I'll hopefully summarize with some sort of kind of compare and contrast of the strengths and perhaps challenges that one faces when using spatial versus temporal domain methods. Okay. So clearly, these two domains have certain situations where they have advantages over the other. So this is my own version of the slide that I think you've seen from both David Kuch's talk yesterday and Bruce's talk this morning, which introduces, in my case, on the left-hand side, kind of spatially resolved reflectance measurements in real space, and on the right, the analog of that in the frequency domain, and in the bottom left-hand side, temporally resolved reflectance, and the analog in the frequency domain being temporal frequency domain reflectance. And so yesterday we focused our time and effort on understanding the characteristics of spatial domain measurements. And I just want to summarize that where in kind of measurement space one has sensitivity to the optical parameters of interest. So generally, in spatially resolved reflectance, you illuminate the target with a narrow beam of light. You measure the reflectance at multiple distances away. Generally, as you move away from the source, as you increase your source detector separation rho, the photons that you're capturing have traveled and increased optical path length, and it's not simply the linear distance, but it's convolved with the number of scattering events and the scattering path length that the photons have traveled before escaping. So generally, you're going to have increased optical path length with increasing source detector separation. Generally, you're going to have more sensitivity to the scattering coefficient very close to the source at source detector separations comparable to the transport mean free path. And generally there, if you increase your scattering coefficient, it will result in an increase in your reflectance. And we saw that in the lab yesterday. As you move further and further away from that source on spatial scales much larger than the transport mean free path, increases in absorption or scattering will lead to a reduction of your reflectance. Absorption because, of course, it extinguishes the light directly, and μs because increases in μs will increase your optical path length between source and detector for source detector separations greater than L star. So typically you want to have detector locations kind of roughly on spatial scales comparable to L star, and detectors larger than L star in order to get optimal separation and sensitivity to both scattering and absorption. The analog of this is in the spatial frequency domain. In the Fourier space is the spatial frequency domain imaging, and here you're, of course, illuminating the target with bands of light with different spatial periodicity. or spatial frequency. And what we learned there is that actually at small spatial frequencies, you tend to have sensitivity to both absorption and scattering, and generally reductions in absorption or increases in scattering result in increases in reflectance. Whereas if you go to larger spatial frequencies, you actually lose sensitivity to absorption and you're only sensitive to scattering. And so one thing that I think I want to emphasize is that we talk about small spatial frequencies and large spatial frequencies. Well, spatial frequency defines a characteristic length scale. So what we mean by small or large spatial frequency is the length scale given by the spatial frequency compared to the length scale of the transport of light. And the length scale that characterizes the transport of light is the transport mean free path, or L star. So what you want to look at is, small spatial frequencies. I'm basically going to use K, and K is really cycles per second. And so typically, if you think of it from a mathematical point, you really want to look at radians per second. So I'm just going to multiply this by 2 pi. So that compares, that gives you kind of the cycle, the radians per second or radians per length scale, excuse me, of the modulated illumination. This is small if it is smaller than the characteristic length scale of light transport. And of course, this is not a length scale, this is a reciprocal length scale, so I have to do 1 over L star. Okay. So if I just bring the L star to the left-hand side, you get what I wrote on my slide, which is just that this has to be less than 1. Okay? So that's what small means. Okay? And so we again see this different domain of being actually sensitive to both mu A and mu S prime at low spatial frequencies, which in some sense is analogous to being at large source detector separations, and only sensitive to mu S at large spatial frequencies, which is analogous to small source detector separations. And we're going to see similar parallels in the temporal domain as well. And so as Bruce said, the temporally resolved reflectance, essentially you put in a delta function in time, a very short pulse, typically on the picosecond scale, and then you measure the temporal dispersion of that light at locations offset from the point of illumination. And typically there's some transit time for the light to get from source to detector. So there's a delay, and then you see some sort of impulse coming out that is spread out in time. And if you go to larger locations in space, then of course that you're going to see attenuation and actually further temporal dispersion. And then in the temporal frequency domain, this impulse of light is replaced by an intensity modulated source in time, and then you can measure an amplitude to decay with temporal frequency and accumulation of phase. Okay, this is sort of called photon density wave. Okay, so let's see how we can analyze these things mathematically. I won't go through this slide in detail. We saw this yesterday, how we started with the radiative transport equation, introduced this very simple 2-term approximation for the angular distribution of the radiance, the single scattering phase function, and the source term in terms of an isotropic term plus a cosine theta term, the first 2 Legendre polynomials. You can put that into the radiative transport equation. You get this diffusion-like equation, but it is different from diffusion because you have an explicit loss term, which you don't have in diffusion, and actually you also have a wave-like propagation term, which is also absent in diffusion equations. And of course, in this P1 or diffusion approximation, since you integrate over all angles and you integrate both the radiance as well as the first moment of the radiance, you lose all information with respect to the anisotropy of the scattering function. Okay. So let's just look at this, what happens when you look at spatially resolved reflectance. I mentioned that we have a common solution to this for a point source that's in the steady state domain. We can essentially reduce the governing equation to this equation in the case of steady state for a point source that can be spatially distributed like a collimated beam, because we have collimated beams to illuminate the sample for spatially resolved reflectance, and we allow a spatial decay in depth of this collimated beam according to essentially the transport mean free path. And the analytic form of the solution of dumping in this source into this equation is actually quite extensive. Here's the reference here. I won't go through the mathematics, but essentially you convolve this source with the Green's function, which is the solution to a point source, to get the solution to that equation. And so, and then you fooled around with this yesterday, but essentially you're insensitive to absorption at short source detector separations. You're more sensitive to absorption at large source detector separations, and the standard diffusion approximation works very well for high ratios of scattering to absorption and less well for more absorbing media, okay? And you experienced that in your exercise yesterday. So let's move our attention to temporally resolved radiative transport. So we have this full equation. Typically, in many cases, this wave-like propagation term is actually of much reduced importance to the first derivative with respect to time, unless you're looking at very, very, very early time scales. And so often we neglect that, and we just focus on the standard diffusion approximation. So if we retain this first, the second derivative term with respect to time, that's called the P1 approximation. If you ignore that, you get the standard diffusion approximation, and you have this optical diffusivity term that governs the time rate of change, which is linked to the velocity of light related to essentially the reciprocal of the transport mean free path. You can get the solution to this equation, which is shown in this paper here by Josh Fishkin and crew. Here, the analysis approach is very similar. We again use the Green's function for a point source in this diffusion approximation that gives you the resulting fluence distribution for an impulse in both space and time. You can convolve that with the distributed point source. You get an equation that probably would fill 3/4 of this page, which I won't show you, but you can find in the references. But what I want to show with that solution is that there are two important limits to this equation, and which actually makes computation of optical properties very easy. So first, if you look at that equation and you look at source detector separations that are much, much longer than the transport mean free path. Okay, so you say, okay, let's not worry about the very early arriving photons. You let the photons interact with the medium and come out. That long equation reduces to a very, very simple equation, which basically relates the time derivative of the natural log of the reflectance becomes this very, very simple equation. And you can then leverage this equation in two ways. You can actually say, well, let's look at what this equation looks like for large times. And you can see, obviously, when you have large times, both the first and the third term drop out, and you see that the time derivative, the time rate of change of the natural log of this reflectance, is linked directly to the absorption coefficient. And it has no sensitivity to the scattering coefficient. So this is nice. It tells you, well, if I just look at the slope of the natural log of this reflectance, I can basically pull out mu a, okay, very easily. The other thing is that when you take this time derivative and you set it to 0, you find out the time at which the reflectance reaches a maximum value, okay? So, and if you find that time and call it T max, you'll find out that you can actually solve for mu s prime, assuming that you know mu a. Well, you can get mu a, right? Instead of looking at where the reflectance is a maximum in time, you look at long times, you get mu a first. Now that you fix mu a, you can get mu s prime. So this is what was done early in this field in the late 80s. If you're able to measure this time temporal dispersion of this reflectance, you can very easily get fairly good estimates for both absorption and scattering. Okay. So it's a fairly smart approach. So let me just show you kind of, again, how these curves look like and comparing them to Monte Carlo simulations. So here I'm looking at a source detector separation of 10 L star, or roughly 10 millimeters, and looking at targets with various ratios of scattering to absorption. And again, we're using the standard diffusion approximation. This should really work best when scattering is dominant over absorption. And you see a number of things. Number one, you see that the standard diffusion approximation actually predicts a time of flight of these photons faster than the actual delay time before you start to see photons coming out of your detector. And this is because you only have a first derivative with respect to time in your equation, which actually violates causality. You actually have an infinite speed of propagation of your photon wave because you don't have a wave-like propagation characteristic. So the standard diffusion approximation predicts early arrival times regardless of your set of optical properties. The standard diffusion approximation also kind of underestimates the time at which the signal reaches its peak by a bit. And that will affect in some sort of a misestimate in your of your recovered scattering properties. But you see for highly scattering materials, you see that it actually gives you a fairly good slope. But even for once you get slightly more absorbing, the slopes actually start to be inaccurate. But that's to be expected because we know that the standard diffusion approximation shouldn't work well for the highly absorbing materials. Here, if you look very close to the source, say at 1 transport mean free path, again, at early times you don't do so well, but you still see that the slopes are actually pretty well predicted by the standard diffusion approximation. That's even because you are close to the source. If you're looking at large times, it means that you've actually looking only at those photons that have multiply scattered, even though you are spatially close to the source. So in spatially resolved, you're just integrating all the photons, and you're dominated by the photons that that come out early, because you can see that the photons that come out early are maybe 1,000 times stronger than the light that comes out late. But if you are able to time gate and only look at the photons that come out late, close to the source, those photons have traveled enough, have undergone enough multiple scattering that actually the diffusion approximation works again. Okay? Okay. So, and then you can look see this a little bit more clearly if you just fix your attention on a highly scattering media and just look at how these curves look like for various source detector separations. And you clearly see, obviously, the further you move away, the less light you have. That regardless of where you are in detection location, you still pretty much match the decay, the temporal decay of the light, and that invariably you do kind of underestimate the time for the peak signal. One thing I just want to emphasize is that you know, the temporal resolution that you need to make these measurements is pretty high, right? This x-axis maximum is 300 picoseconds. So the instrumentation needed to do this in the early days was very, very challenging. Using picosecond pulses for your incident source and microchannel plate PMTs on detection. Okay, so the early pioneers in this field really had a lot of technical challenges to face. Okay, great. Any questions on this? Okay, and then you can see similar things for highly absorbing media, and the reason I put this up is you know, the basic shape is the same. You don't see as much differences between source detector separation as far as your intensity, but one thing I want to just emphasize is the huge dynamic range in the signal. So obviously you're not going to do very well trying to look at a highly absorbing medium using this technology, because the dynamic range of your measurement is clearly impractical for even our modern day detector technologies. You need 10 to 15 orders of magnitude in dynamic range, which is not tractable. Okay, so now let's move to the temporal frequency domain. Maybe I'll pause just to see if there are any questions on the time result measurement. Okay, so the time-dependent P1 approximation, we've seen this equation before. So to get this, a solution to this equation in the temporal frequency domain, what we do is that we assume harmonic waveforms for both the fluence rate and the source. So essentially, we have an AC component of this fluence rate with some sort of modulation frequency omega. And of course, we're intensity modulating our source with also a temporal frequency omega. If you put that into this equation and you only look at the AC term of that equation, you get this P1 approximation in the temporal frequency domain, where you're actually just looking at the temporally modulated portion of the fluence rate. And the equation looks exactly the same as the steady state, except this attenuation coefficient, this mu effective, has not only a dependence on your optical properties, mu effective, so which is what we saw in the DC case, but then you have these other contributions which relate the intensity modulation frequency with characteristic relaxation times within your media. So there are two relaxation times of importance in this case, and I denote them the absorption relaxation time, which Bruce mentioned. And the absorption relaxation time is simply the time it takes light on average to propagate in the material before it encounters an absorption event. So the characteristic length scale of that is 1 over mu sub A, right? That's your length scale for absorption. And you have to divide that by your velocity in the medium. So that will be times 1 over v, okay? And so your velocity in your medium, if you assume a refractive index mismatch of about 1.4, the speed of light in tissue is about 2.1 times 10 to the 8th meters per second, okay? And if you are in a low absorbing tissue such as breast, a characteristic mu sub A value is about 5 times 10 to the minus 3 per millimeter, okay? And if you go through the numbers, that results in an absorption relaxation time on the order of 1 nanosecond, okay? So if you think about the time it takes for the average photon to get extinguished in a low absorbing tissue, it's about 1 nanosecond. Now, the other characteristic time scale that's important that I don't think Bruce mentioned is what's called the transport relaxation time. So this is the characteristic time before the photons interact with the tissue, either through absorption or scattering, okay? And so there, you replace 1 over mu sub A with the transport mean free path, or L star, so you can think of L star over V, or if you want to write it in terms of the optical properties, you get 1 over mu A plus mu S prime, okay, times 1 over V. Does anybody have an estimate off the top of their head of how different? So is that time scale going to be faster or slower than the absorption relaxation time in a typical highly scattering media? It'll be much faster, right? And if you imagine that your characteristic scattering coefficient is, say, 1 compared to 5 times 10 to the minus 3, you can imagine that that's going to be about 5,000 times faster. So this is about 5 picoseconds. Okay. So it's the interplay between interaction, which will redirect and redirect the photon density wave, and actually it acts as a multiplier for the photon path length. And that interaction with the characteristic timescale for absorption that really gives rise to the intrinsic physics of the propagation of photon density waves in these tissues. Okay? So to solve this equation, you can adopt this basic functional form for the modulated fluence rate. So you basically have an exponential decay in the real domain, which expresses the attenuation of that wave, and then you have an exponential decay in the imaginary space, in some sense, that communicates the phase accumulation of that wave as it propagates. And you can solve for both the k real and the k imaginary. This is the general. This can get simplified a little bit if you assume that your modulation frequencies are small, and in this domain, your modulation frequencies are small when this limit of the square of the modulation frequency times the product of the absorption and scattering relaxation times is much, much less than 1. If you actually do this computation, you'll find that this, for these optical properties, this characteristic modulation frequency is about 2 gigahertz, which is much higher than the typical modulation frequencies of hundreds of megahertz that are used. And in that limit, you can reduce the complexity of this equation a little bit and come up with the characteristics that Bruce mentioned earlier. So here what I've done is I've actually flipped the curve that Bruce showed you earlier. He had modulation frequency on the y-axis and the k real and k imaginary on the x-axis, which I think is how electrical engineers actually visualize their k real and k imaginary. But in practicality, your independent variable is modulation frequency. This is what you have direct control over experimentally, and you want to see how the attenuation changes. So let's look at highly scattering media. So here you see that for highly scattering media, you have some sort of decay or attenuation with the depth, and that slightly increases once you start to probe on modulation frequencies faster than the absorption relaxation time. So here I've chosen a mu A of 0.01 that corresponds to an absorption relaxation frequency of about 350 megahertz. So you start to see that this is fairly flat, and then you start to grow in your damping of the wave. So essentially you penetrate very, very deeply in tissue, but you start to attenuate slightly more once you are using modulation frequencies that are a bit higher than the corresponding absorption relaxation time. With respect to the phase accumulation, this is actually fairly linear before you reach the absorption relaxation frequency, and then you start to get basically a damping of this increase of k imaginary with modulation frequency. And what this means is that since you're increasing linearly, the k imaginary is increasing linearly with modulation frequency, it means that as your modulation frequency doubles, your phase accumulation doubles. So it basically means that you're in a linearly propagating regime in terms of phase accumulation. And then you start to accumulate less and less phase as you propagate. And that's because you're starting to kill off photons. Here, essentially, you're not killing off that many photons because you're basically the intensity modulation is slower than this absorption relaxation time. And therefore, you're really not depleting the photons. All the photons you're getting out have essentially traveled the same transport mean free path. Whereas as you start to modulate faster, you're actually killing off photons that have traveled long path lengths, and therefore you're not accumulating as much phase because you're killing off the photons selectively that have traveled a longer path length. So that's where you see this nonlinearity or this dispersive quality of the propagation of the photon density waves, and that's where you get differential sensitivity to absorption versus scattering. So you really need to probe across this frequency scale relative to the absorption relaxation time. Okay? And a way to see that is looking at sensitivities. So if you look at the sensitivity of these attenuations, both in amplitude and in phase, with respect to absorption, what you see is of course, as you increase absorption, you're going to increase the dampening of your photon density wave. This is the amplitude. And you see that actually you're most sensitive at very low modulation frequencies to absorption. And that sensitivity actually drops off as you increase your modulation frequency. You see also that your accumulation of phase actually drops. So your derivative of K imaginary with respect to absorption is actually negative, which means that at increased absorption, you're actually going to actually accumulate less phase. And that actually the peak sensitivity to absorption relative to your phase measurements occurs at a frequency that is roughly comparable to the absorption relaxation frequency. Okay? So, so clearly, if you look at just the intensity of your photon density wave, you're most sensitive to absorption through the amplitude at low modulation frequencies. With respect to phase accumulation, you'll find that actually you're not sensitive to phase accumulation very much, or sensitive to scattering through phase, but you're actually very sensitive to scattering at low modulation frequencies through the amplitude. But as you go to higher and higher modulation frequencies, you actually get more and more sensitivity to scattering. But you're also sensitive to absorption. But if you can get absorption here through your amplitude, you're able to actually then separate absorption from scattering. And that's the key thing that you need to accomplish. So, so that's actually all I want to go through this morning. We're able to kind of fill out this quad diagram, so to speak, for kind of the rules of thumb for how optical path length and how sensitivity to optical properties differ when you're looking at temporally resolved reflectance versus temporal frequency domain. Basically, at early times in temporally resolved reflectance, you're very sensitive to scattering but not absorption. And at very late times, you're sensitive to absorption but not so much scattering. And so that's a good way of being able to separate the two. And with respect to temporal frequency domain methods, at small temporal modulation frequencies, you can be very sensitive to absorption but not so much to scattering. And it's only when you start to modulate on temporal frequencies that are comparable or larger to the absorption relaxation time that you actually are able to separate impacts of scattering relative to absorption. And you're going to see that today in today's laboratory. And so that's why you see actually that the most kind of effective application of the frequency domain is in tissues such as breast, where you have very, very low absorption because you don't have to modulate your sources as high in order to get sensitivity to absorption. Once you go into muscle or brain, things get more challenging. Not that it's not possible, but it just gets more challenging instrumentation-wise. Okay? So with that, I'm just going to end, and I'm happy to field any questions you have. Okay? It's Friday. We made it through 5 days of lectures. That's good. Is anybody working on temporal frequency domain in this group? Partially, yeah. And I know Professor Pogue has a fairly, at least he used to have a fairly large effort in doing breast imaging, right? And breast image reconstruction with these multiple fiber optic arrays, right, going circumferentially around the breast to do. Good, so at least a couple of groups. Okay, well, I'll be around. You know where to find me if you have questions about this, and maybe the demos that you'll see this afternoon as well as the labs will stimulate more questions. So thank you, and picnic starts at noon, right?
Yes.
Very good. Okay.